Section: Introduction. In this section, we explore the fascinating capabilities of human imagination, which allows us to create detailed fictional scenes, like a blue emu swimming in the ocean. This imaginative process involves combining various concepts and predicting realistic aspects of the scene, such as its physics and sound. Our goal is to equip AI systems with similar generative and predictive abilities, which presents a significant scientific challenge with wide-ranging applications. While large language models focus on text, we shift our attention to media, specifically images, videos, and audio. We introduce MovieGen, a collection of foundational models for media generation. These models can create high-quality images, videos, and audio, and they can also personalize videos based on user input. For instance, MovieGeneral can generate videos from text prompts, align videos with characters from reference images, and produce videos with synchronized audio. We have found that by increasing the training data, computational resources, and model parameters of a simple transformer-based model trained with flow matching, we can achieve high-quality generative models for video and audio. Our models are pre-trained on a vast amount of internet data, with our largest text-to-video model, MovieGeneral Video, having 30 billion parameters, and our largest video-to-audio model, MovieGeneral Audio, having 13 billion parameters. We also enhance MovieGeneral Video to create personalized MovieGeneral Video, which generates videos tailored to a specific person's face. Additionally, we introduce MovieGeneral Edit, a new post-training method that allows for precise video editing. Together, these models can produce realistic, personalized HD videos lasting up to 16 seconds at 16 frames per second, along with 48 kHz audio, and they can edit both real and generated videos. MovieGeneral sets a new standard in various media generation tasks, outperforming existing commercial systems in text-to-video generation and audio generation. We also publicly release 2 benchmarks to facilitate future research: MovieGen Video Bench and MovieGeneral Audio Bench. We provide comprehensive details on our model architectures, training processes, and experimental setups to support further advancements in media generation. In summary, MovieGeneral models can generate videos with synchronized audio, personalized characters, and support video editing. We achieve these capabilities through 2 foundational models: MovieGeneral Video, which generates high-quality HD videos based on text prompts, and MovieGeneral Audio, which produces high-quality audio synchronized with video. Both models are pre-trained on extensive datasets, allowing them to understand complex visual and audio relationships. We enhance MovieGeneral Video with personalization and editing features, enabling users to create videos that reflect specific individuals and to perform precise edits using text instructions. Section Summary. In this section, we introduce MovieGen, a suite of foundation models designed for high-fidelity media generation, including video and audio, from text prompts. Our models, which include MovieGeneral Video and MovieGeneral Audio, excel in generating personalized videos and synchronized audio, outperforming existing commercial systems and enabling new capabilities in video personalization and editing. Section: Joint Image and Video Generation. In this section, we describe our approach to joint image and video generation using a single foundation model called MovieGeneral Video. This model takes a text prompt as input and produces a video made up of multiple RGB frames. We consider images as single-frame videos, allowing us to use the same model for both tasks. Since paired image-text datasets are easier to gather and cover a wider range of concepts and styles, this joint modeling enhances our model's generalization capabilities. Our training process is organized into several stages for efficiency. Initially, we pre-train the model on low-resolution images, then proceed to joint pre-training with both low-resolution images and videos, followed by high-resolution training. We fine-tune the model on high-quality videos to enhance the output. Additionally, we incorporate features like personalization and editing through post-training. To improve training and inference efficiency, we generate outputs in a compressed latent space. We achieve this by training a temporal autoencoder, TAE, that maps both RGB images and videos into this compressed space. We encode the text prompt using pre-trained text encoders to create embeddings that guide our model. Our generative model uses a flow-matching training objective, taking sampled noise and the provided embeddings to produce an output latent representation. This latent output is then decoded back into pixel space to generate the final image or video. We prioritize simplicity in our design choices, including the training objective and model architecture. For instance, we use the Llama 3 backbone architecture, which allows us to scale the model effectively while maintaining efficient training. Our largest model, with 30 billion parameters, can generate videos in various aspect ratios and lengths, with a resolution of 31 pixels, which can be further enhanced to full HD 1080p. Next, we outline the key components of the Movie General Video Model, including the TAE, the training objectives, and our scaling techniques. The TAE compresses RGB videos and images into a learned latent space, enabling efficient video generation. We utilize a variational autoencoder structure for the TAE, which compresses input videos into a continuous latent representation, reducing the sequence length for our transformer backbone. This design choice simplifies our model by eliminating the need for frame interpolation. In terms of architecture, we enhance image autoencoders by adding temporal parameters, allowing us to process videos of any length, including treating images as single-frame videos. We find that increasing the number of channels in the latent space improves performance, and we initialize spatial parameters using a pre-trained image autoencoder before jointly training on images and videos. We also address issues with our training objective that led to artifacts in the generated videos. Instead of altering the model architecture, we introduce an outlier penalty loss to discourage the model from encoding extreme latent values. This adjustment, combined with standard variational autoencoder losses, effectively removes the artifacts. For efficient inference, especially with high-resolution long videos, we implement a tiling strategy. We divide the input video and latent tensor into smaller segments, process each segment, and then stitch the results together. This method allows us to manage memory requirements while maintaining quality, using overlapping tiles and blending techniques to minimize boundary artifacts. Section Summary. In this section, we present Movie General Video, a joint foundation model that generates both images and videos from text prompts by treating images as single-frame videos. We detail our training process, which includes pre-training on low-resolution data, the use of a temporal autoencoder for efficient spatiotemporal compression, and improvements to the training objective to mitigate artifacts, ultimately enabling the generation of high-quality videos at various resolutions and aspect ratios. Section: Training Objective for Video and Image Generation. In this section, we describe our training objective for generating images and videos using the flow matching framework. This approach allows us to create samples from our target data by gradually modifying samples from a prior distribution, like a Gaussian distribution. During training, we take a video sample from the latent space, select a time step, and generate a noise sample to create a training sample. Our model learns to predict the velocity, which helps it adjust the training sample towards the video sample. We have various methods to construct the training sample, but we opt for simple linear interpolation or the optimal transport path. The true velocity can be derived from our model parameters and the text prompt embedding, and we train the model by minimizing the difference between the true velocity and our predictions. We sample from a logit normal distribution, where the underlying Gaussian has a mean of 0 and a standard deviation of 1. During inference, we first sample the noise and then use an ordinary differential equation, ODE, solver to compute the video sample based on our model's predictions. We choose a straightforward first-order Euler-ODE solver with a specific set of time steps designed for our model. The time step we select influences the signal-to-noise ratio, SNR, and our interpolation method ensures that the model receives pure Gaussian noise during training, allowing it to make accurate predictions during inference. We note that many video generation models rely on diffusion formulations, and recent studies highlight the importance of selecting appropriate diffusion noise schedules with a zero-terminal SNR for effective video generation. Our flow matching implementation naturally achieves this zero-terminal SNR, making it more robust to noise schedule choices and outperforming diffusion losses. Next, we discuss our joint image and video generation architecture. We generate in a learned latent space representation of the video, which we prepare for the transformer backbone by using a 3D convolutional layer to create patches and then flattening them into a sequence. This process results in a specific number of tokens for the transformer. We utilize a factorized learnable positional embedding to accommodate various input sizes and video lengths. We convert the patch tokens into separate embeddings for spatial and temporal coordinates and calculate the final positional embeddings by combining all factorized embeddings. By adding these embeddings to all transformer layers, we reduce distortion and artifacts, especially in the temporal dimension. Our transformer backbone is based on the Llama 3 architecture, incorporating RMS norm and SWI glue. We make three key modifications for video generation. We add a cross-attention module to connect the self-attention and feed-forward network, use multiple text encoders for their strengths, and include adaptive layer norm blocks to integrate the time step. We also employ full bidirectional attention instead of causal attention. We intentionally keep our architecture simple and similar to large language models, LLMs, to facilitate scaling. Our design has shown to perform comparably or better than specialized architectures from previous work while being more stable across various hyperparameters. We provide key hyperparameters for our largest model and illustrate the transformer block with details on feature dimensions. Section Summary. In this section, we describe our use of the flow matching framework to train a joint image and video generation model, which involves predicting the velocity of samples in latent space to align them with video data. We also outline our transformer backbone architecture, which incorporates text conditioning and adaptive layer normalization, allowing for effective scaling and stability during training while maintaining high performance. Section: Rich text embeddings and visual text generation. In this section, we discuss how we utilize pre-trained text encoders to transform our input text prompt into a text embedding, which serves as the input for our video generation system. We combine three text encoders, UL2, BYT5, and long prompt metaclip, to achieve both semantic and character level understanding. The long prompt metaclip model is fine-tuned on longer captions to extend the input text length. We merge the text embeddings from these encoders after applying linear projection and normalization to ensure they fit into the same dimensional space. The UL2 and long prompt metaclip encoders generate prompt-level embeddings with distinct characteristics. UL2 is trained on a vast amount of text data, enhancing its reasoning capabilities, while long prompt metaclip aligns text representations with visual ones, aiding in cross-modal generation. The BYT5 encoder focuses on encoding visual text, specifically parts of the prompt that request character strings in the output. To manage the length of our generated videos, we prepend the desired frames per second (FPS) value to the input text prompt. During pre-training, we sample video clips at their original FPS, with a minimum of 16 FPS, and during fine-tuning, we use fixed FPS values of 16 and 24. Our pre-training dataset includes 100 million video text pairs and 1 billion image text pairs. We follow a similar curation strategy for both video and image data. Our initial data pool consists of videos ranging from 4 seconds to 2 minutes, covering various concepts like humans, nature, and objects. We filter these videos through 3 stages: visual filtering, motion filtering, and content filtering, followed by a captioning stage. Each filtered clip is annotated with detailed captions averaging 100 words. In the visual filtering stage, we apply 6 filters to eliminate low-quality videos, ensuring a mix of landscape and portrait formats. We also use a video OCR model to remove clips with excessive text and extract segments of 4 to 16 seconds. Motion filtering involves removing videos with no motion and those with excessive jitter. Content filtering ensures diversity by eliminating duplicate clips and resampling to balance dominant concepts. For captioning, we use the Llama 3 video model, fine-tuning its variants for video captioning. We also train a camera classifier to predict camera movements, which we incorporate into the captions for enhanced control during video generation. We curate 3 subsets of pre-training data with increasingly strict visual and content standards. Our high-resolution set consists of 80% landscape and 20% portrait videos, with a focus on clips featuring humans. We categorize our training data by aspect ratio and length, allowing for efficient batching. This enables our model to generate videos of various sizes and frame rates, enhancing its versatility. Section Summary. In this section, we describe our approach to generating videos from text prompts using pre-trained text encoders, specifically UL2, BYT5, and long prompt metaclip, which provide diverse text embeddings for video generation. We also detail our extensive pre-training data curation process, which includes filtering for visual quality, motion stability, and content diversity, ultimately resulting in a dataset of high-quality video text pairs for effective training. Section: Training. In this section, we describe the training details for our 30 billion parameter model. To enhance training efficiency and scalability, we utilize a multi-stage training approach. This consists of 3 main steps. First, we conduct initial training on the text-to-image (T2I) task. Second, we perform joint training on both text-to-image and text-to-video (T2V) tasks. And third, we progressively scale the resolution from low-resolution 49 by 49 pixel data to high-resolution 5 by 5 pixel data. We also engage in continuous training with improved datasets and optimized methods while considering compute and time limitations. We keep a validation set of unseen videos and monitor the validation loss throughout the training process, noting that this loss correlates well with visual quality as judged by human evaluations. For the text-to-image warm-up training, we find that joint training of T2I and T2V models is significantly slower and requires more memory than training T2I models alone, mainly due to the longer latent token length. We also observe that starting T2I-V models from scratch leads to slower convergence compared to initializing from a T2I model. Therefore, we begin with a T2I-only warm-up training stage at a lower resolution of 256 pixels, allowing us to use a larger batch size and more training data. After the T2I warm-up, we proceed to joint training for T2I and T2V. To facilitate this, we double the spatial positional embedding layers to handle different aspect ratios and add new temporal layers for up to 32 latent frames. We initialize the spatial layers from the T2I model with a 93 by 93 expansion. We start with 256 pixel resolution images and videos for this joint training, and for the 768 pixel stage, we expand the spatial layers by 105 by 105. During the 256 pixel T2I-V stage, we use a large batch size of 1536 samples and a higher learning rate, which leads to stable training. After 123,000 iterations, we double the number of GPUs, resulting in a larger global batch size and a significant drop in validation loss. We stop training at 185,000 iterations after processing 395 million video samples. In the 768 pixel T2I-V stage, we notice that the validation loss decreases quickly in the first 10,000 iterations and then fluctuates. We reduce the learning rate by half at 19,600 iterations, which further decreases the loss. We continue training and lower the learning rate whenever the validation loss plateaus. For fine-tuning, we enhance the aesthetic quality of the generated videos by fine-tuning the pre-trained model on a small set of carefully selected videos. This fine-tuning set is manually curated, and we refer to this stage as supervised fine-tuning. During this phase, we train multiple models and combine them through a model averaging approach. While our model generates high-quality images, we find that post-training specifically for images significantly boosts quality. In collecting fine-tuning video data, We aim for high-quality videos that exhibit good realism, aesthetics, and a variety of concepts, along with high-quality captions. We start with a large pool of videos and apply both automated and manual filtering steps. This process involves 4 key stages. First, we establish a set of candidate videos using automated filters. Second, we balance the concepts in the video set. Third, we manually identify cinematic videos. And fourth, we manually caption the videos, refining generated captions to ensure accuracy and detail. In the supervised fine-tuning stage, we use the same model architecture as in pre-training, initializing with pre-training checkpoints. Unlike pre-training, which uses large-scale data and resources, we use a smaller batch size and 64 nodes to train the model, employing a cosine learning rate scheduler. For videos lasting 16 seconds, we train at 16 frames per second, and for those between 10.6 and 16 seconds, we train at 24 frames per second, ensuring our model effectively supports video generation in both durations. Our experiments show that the choice of fine-tuning data, hyperparameters, and pre-training checkpoints significantly impacts the model's behavior, including realism, consistency, and camera control. To leverage the strengths of these models, we adopt a model averaging approach, similar to Llama 3, averaging models obtained from various fine-tuning experiments. Section Summary. In this section, we detail our multi-stage training procedure for a 30B parameter model, which includes initial text-to-image training, joint text-to-image and text-to-video training, and progressive resolution scaling, all while monitoring validation loss to ensure visual quality. We also describe our supervised fine-tuning process, which involves curating high-quality video data through automated and manual filtering, followed by model averaging to enhance the final model's performance. Section: Inference. In this section, we outline the various hyperparameters and settings we used for sampling from Movie General Video. To compare with previous work, we set a text classifier free guidance scale of 7.5 and employed a linear quadratic sampler with 50 steps, which is equivalent to 250 linear steps. We also implemented an inference prompt rewrite on the input text prompt. For the inference prompt rewrite, we trained our model using high-quality video and image text pairs, characterized by detailed descriptions and consistent paragraph structures. However, we noticed that prompts during inference often vary significantly in style and length, with most users typically writing less than 108 words, which is shorter than our training captions. To address this gap, we utilized Llama 3 to enhance the original input prompts, making them more detailed. Our approach involved using a standardized structure to rephrase prompts, ensuring visual consistency. We simplified complex vocabulary to improve clarity and understanding. We found that overly detailed descriptions could introduce artifacts in the generated videos, emphasizing the need for a balance between richness and visual quality. To enhance the efficiency of our inference rewrite model, we developed a teacher-student distillation method. We first created a teacher model based on the Llama 370B model, using detailed prompt instructions and examples from the training set. We then collected human-in-the-loop fine-tuning data by using the teacher model to evaluate a large pool of prompts and selecting high-quality rewrites based on human feedback. Finally, we fine-tuned an 8B Llama 3 model on these selected pairs to create a final prompt rewrite model, reducing latency in the system. For improving inference efficiency, we designed a linear quadratic T-schedule. We observed that the most significant changes in model inputs and outputs occur early in the inference steps. Therefore, our scheduler copies the first 25 low-time steps and connects the remaining steps with 25 quadratic steps. To sample videos efficiently, we used the Euler sampler with a unique T-schedule tailored to our model. We found that Euler outperformed other solvers like Midpoint or adaptive solvers. We also noted that reducing inference steps for video generation is more complex than for images due to the additional time dimension, making the quality and alignment of generated videos more sensitive to the number of steps. For instance, videos generated with different numbers of linear steps, such as 250, 500, or 1000, showed noticeable differences in quality and scene composition. While techniques like distillation can speed up inference, they require additional training. We discovered a straightforward inference-only technique that can achieve significant speed improvements with minimal code. We found that we could closely replicate the quality of a 55-step video generation process using just 50 steps by applying a linear quadratic t-schedule. This method follows the first 25 steps of a 55-step linear schedule and approximates the remaining steps with 25 quadratically spaced steps. In practice, we use a 50-step linear quadratic schedule to emulate 113 linear steps for optimal results, as the early inference steps are crucial for setting up the scene in the video. Section Summary. In this section, we detail the hyperparameters and settings for sampling from Movie General Video, utilizing a text classifier free guidance scale of 7.5 and a linear quadratic sampler with 50 steps. We also introduce an inference prompt rewrite model that enhances prompt clarity and consistency by transforming user inputs into more detailed descriptions, while employing a teacher-student distillation approach to improve computational efficiency and reduce latency in video generation. Section: Evaluation. In this section, we explain how we evaluate the quality of text-to-video generation for Movie General Video and other models. Our aim is to create clear and effective metrics that highlight a model's weaknesses and offer reliable feedback. We discuss various evaluation axes and their design motivations, and we introduce our new benchmark, MovieGen Video Bench. Throughout our work, we rely on human evaluations to assess the quality of generated videos across different axes. For each axis, we conduct pairwise A/B tests where expert evaluators compare two videos side by side. They choose a winner based on the specific axis or declare a tie if there is no clear winner. We also discuss the reasons for using human evaluations and the limitations of existing automated metrics. When it comes to evaluation axes, we face unique challenges in text-to-video generation due to the added complexity of time. A high-quality video must accurately reflect the provided text prompt, maintain visual quality across frames, and be visually appealing with a realistic style. We evaluate generated videos based on three main axes: 1. Text alignment, 2. Visual quality, and 3. Realness and aesthetics. For text alignment, we assess how well the video matches the prompt, which can include details about the subject, background, camera, lighting, and style. Evaluators focus on these aspects and provide feedback based on two sub-axes: subject match, which looks at the alignment of appearance and background, and motion match, which evaluates the alignment of motion-related descriptions. In terms of visual quality, we focus on the model's ability to generate consistent and natural motion. We propose four sub-axes to capture this: frame consistency, which checks for temporal consistency and the absence of artifacts; motion completeness, which measures whether the video has enough motion; motion naturalness, which evaluates the realism of movements; and overall quality, where evaluators choose the video with the best overall quality based on the previous metrics. For realness and aesthetics, we assess the model's ability to create photorealistic videos with appealing content. We ask evaluators to consider two sub-axes: realness, which measures how closely a video resembles a real one, and aesthetics, which evaluates the visual appeal of the content, lighting, and style. Evaluators provide reasons for their choices in both categories. Section Summary. In this section, we outline our evaluation approach for the text-to-video quality of Movie General Video and other models, focusing on establishing effective metrics to identify weaknesses and provide feedback. We utilize human evaluations across three main axes: text alignment, visual quality, and realness and aesthetics, through pairwise A/B tests, ensuring a comprehensive assessment of generated videos. Section: Evaluation Benchmark. In this section, we introduce our evaluation benchmark, called MovieGen Video Bench, which includes 1,003 prompts designed to assess various aspects of video generation. To ensure fair comparisons with Movie General Video in future studies, we also provide unselected generated videos from Movie General Video within this benchmark. Our benchmark is significantly larger than those used in previous research, being over 100 times bigger. We focus on prompts that explore several key areas. 1. Human activities. 2. Animals. 3. Nature and scenery. 4. Physics concepts like fluid dynamics and gravity. And 5. Unusual subjects and activities. Each prompt is tagged with a quality level of high, medium, or low. We present examples of these prompts and their distribution across different concepts. We evaluate the model's performance using the entire set of prompts and analyze the results based on specific metrics. Prompts featuring unusual subjects help us assess the model's ability to handle content that is outside the usual distribution. Next, we discuss our experiments and results for Movie General Video. We compare our findings with previous text-to-video generation work and examine key design choices for Movie General Video. We also evaluate the TAE and the spatial upsampler. For comparisons, we use unselected videos from the Movie Gen Video Bench prompt set for prior methods and compare them with unselected videos from Movie General Video. This includes commercial models like Runway Gen 3 and Luma Labs, as well as closed-source methods like OpenAI Sora, where we rely on their publicly available examples. To ensure fairness, we manually select one video from 5 generated by Movie General Video for each prompt when comparing with OpenAI Sora. We address the challenge of different video resolutions and aspect ratios by downsampling Movie General Video's outputs to match those of the other methods. Detailed information about this process and the comparison with OpenAI Sora can be found in the appendix. We analyze Movie General Video's performance across various evaluation criteria, reporting a net win rate that indicates its strong performance compared to other models. Movie General Video outperforms Runway Gen 3 and Luma Labs significantly, showing notable advantages in naturalness and frame consistency. While it has a moderate win over OpenAI Sora, it performs comparably with Kling 1.5. In terms of realism and aesthetics, Movie General Video excels against all compared models, demonstrating its ability to create photorealistic and visually appealing content. It also shows strong text fidelity, performing better than OpenAI Sora, Runway Gen 3, and Luma Labs. We showcase several generated videos that illustrate Movie General Video's capability to produce high-quality outputs for both typical and fantastical prompts. The videos depict complex scenarios, such as a firefighter navigating a burning forest or a puppy searching for its owner. We also analyze the correlation between validation loss and human evaluations, finding that lower validation loss corresponds to better performance in evaluations. This suggests that our validation loss can effectively guide model development. Finally, we utilize supervised fine-tuning to enhance video generation quality, showing significant improvements in visual quality and text alignment when comparing pre-trained and fine-tuned models. Section Summary. In this section, we introduce the Movie Gen Video Bench, a comprehensive evaluation benchmark with 1,003 prompts designed to assess various aspects of video generation, including human activities, animals, and physics. We compare our model, Movie General Video, against prior work, demonstrating its superior performance in generating high-quality, realistic videos that align well with text prompts, while also addressing challenges such as resolution and aspect ratio differences. Section: Ablations. In this section, we examine the key design choices for Movie General Video. For all the tests we discuss, we utilize a simpler and smaller training and model setup compared to what we used for our main results. We evaluate the impact of each design choice through human assessments of text-to-video quality on a smaller subset of our dataset, called Movie Gen Video Bench Mini, which includes 381 prompts. We focus on text accuracy and overall quality in our findings. For each test, we keep all model aspects constant except for the design choice we are analyzing to ensure a fair comparison. We start by outlining our simpler baseline setup, which consists of a Movie General Video model with 125 billion parameters, designed to create videos of 126 frames. We employ a technique that compresses data across all dimensions to generate latent representations. This smaller model has 130 layers in its transformer, with an embedding dimension of 132 and 132 attention heads. For our training setup, we follow a two-stage process. First, we pre-train on text-to-image data, and then we conduct joint training for text-to-image and text-to-video. We use a smaller dataset of 21 million videos, all with a consistent landscape aspect ratio. Initially, we train on the image dataset with a specific learning rate and batch size across multiple GPUs for a set number of iterations. Then, we perform joint training with a different ratio of iterations for images and videos, using a learning rate of 500 thousandths for a specified number of iterations. In our first ablation result, we compare the flow matching training objective to a diffusion training objective. We find that flow matching yields better video generations in terms of quality and text alignment, even when controlling for other factors. This finding holds true across various model sizes, leading us to adopt flow matching for our training. Next, we assess the role of video captions in our model. Our model is trained using clips from real videos along with captions generated by our Llama 3 video model. To evaluate the effectiveness of these captions, we compare them to an image-based captioning method that rewrites captions from selected frames of the video. Through human evaluations, we find that captions generated by Llama 3 video are preferred significantly more often than those from the image-based method. We observe that our video captioning model captures finer details of movements, which enhances the training signal and improves prompt alignment. We also analyze our model architecture, which is based on Llama 3, and compare it to a diffusion transformer model commonly used in media generation. Our results show that the Llama 3 architecture outperforms the diffusion transformer in both quality and text alignment. This suggests that Llama 3 has advantages for media generation tasks, and we find no substantial examples in the literature of scaling the diffusion transformer to large sizes. To further explore our model's scaling behavior, we test 4 different model sizes: 5 billion, 9 billion, 17 billion, and 30 billion parameters. We train each model with varying computational resources and measure their validation loss. We plot these results and identify the optimal model size for each compute budget. Interestingly, we find that our optimal models align closely with the scaling laws established for Llama 3, indicating that these laws may be useful for predicting model sizes and compute budgets in media generation as well. Section Summary. In this section, we ablate key design decisions for movie general video using a smaller baseline model to quantitatively assess the impact of various factors on text-to-video generation quality. Our findings indicate that the flow matching training objective and the Llama 3-based architecture significantly enhance video generation performance, while our model's scaling behavior aligns closely with established Llama 3 scaling laws. Section TAE Results. In this section, we present the results and insights from our temporal autoencoder TAE design choices. For evaluation, we report the reconstructed peak signal-to-noise ratio PSNR, structural similarity SSIM, and Frechet inception distance FID, for video clips taken from the training set, with durations of 2, 4, 6, and 8 seconds, each containing 200 examples. We also assess these metrics on a validation split of the image training set, averaging them over video frames. For qualitative results, we display sample reconstructions from our TAE, showing original video frames alongside their reconstructions. We notice that while the TAE can effectively reconstruct video frames, it struggles with high-frequency details, especially in fast-moving videos. When both high-frequency details and larger elements are present, we see a loss of detail in the reconstructions. In our quantitative analysis, we compare our TAE to a baseline frame-wise autoencoder that does not compress temporally. Our baseline also uses an 8-channel latent space, which is standard for frame-wise encoding. We find that the TAE performs competitively with the frame-wise encoder while achieving 13% higher temporal compression. Additionally, the TAE outperforms the frame-wise model on images, likely due to the increased channel size of the latent space. Next, we conduct ablation experiments to explore our TAE model's design choices. For simplicity, we use a TAE model with a smaller compression ratio of 152, producing an 8-channel latent space. We compare 2.5D, 2D spatial followed by 1D temporal, attention and convolutions to 3D spatiotemporal attention and convolutions. Our findings indicate that while 3D attention yields slightly better reconstruction metrics, the improvement does not justify the higher memory and computational costs, so we opt for the 2.5D approach. We also examine the impact of adding an outlier penalty loss, OPL. This addition helps eliminate artifacts in generated and reconstructed videos, enhancing reconstruction performance. We first train a baseline model without OPL for 50,000 iterations, then fine-tune it with OPL for 10,000 iterations, comparing it to a baseline fine-tuned without OPL for 20,000 iterations. The results suggest that OPL fine-tuning improves reconstruction for both images and videos. In terms of spatial upsampling, we present results from our spatial UP sampler, showing a visual comparison of the upsampling process. The results indicate that the UP sampler effectively sharpens and enhances visual details, leading to a more refined output. For text-to-image generation, we train the MovieGen model on both videos and images, enabling it to generate both types. To validate its image generation capabilities, we continue training with an image autoencoder and compare its performance to previous work. In our method for text-to-image generation, we aim to create realistic images. We initialize with the MovieGen model, replacing the TAE with an image autoencoder, and train it on the text-to-image task. The final image resolution is 154 by 154 pixels. After training, we curate 1,000 images created by in-house artists for quality tuning, fine-tuning the model for 6,000 steps with a learning rate of 0.00001 and a batch size of 64, using a constant learning rate scheduler with 2,000 warm-up steps. Section Summary. In this section, we present the results and design choices for our temporal autoencoder, TAE, demonstrating its ability to reconstruct video frames with competitive quality while achieving higher temporal compression compared to a baseline model. We also explore the impact of various design decisions, such as the use of 2.5D versus 3D attention, the addition of an outlier penalty loss to improve reconstruction quality, and the effectiveness of our spatial UP sampler in enhancing visual details. Section: Results. In this section, we assess the quality of our text-to-image generation results using human evaluators who focus on two main aspects: A. How well the images match the text, and B. The overall visual quality. For text faithfulness, we set up a pairwise A-B comparison where evaluators choose which image better represents a given prompt. They decide between options A or B based on text alignment. For visual quality, we use a similar A-B comparison, asking evaluators to identify which image appears more realistic. They look for flaws, such as incorrect numbers of fingers or spelling errors in visual text, before making their choice. To create our benchmarking prompts, we analyzed common user prompts for text-to-image generation, categorized them, and used large language models to generate prompts that resemble real user requests. We compared our results with leading text-to-image models like Flux.1, OpenAI DALL-E 3, Midjourney V6.1, and Ideogram V2, which are commercial solutions that complicate fair comparisons. Like in text-to-video evaluations, we gathered unselected generated images from the benchmark prompts for previous methods and compared them with unselected images from our MovieGen for the same prompts. To ensure a consistent comparison across all models and evaluation criteria, we applied the ELO rating system to rank the models based on battle records derived from raw human evaluations. In our A-B comparisons, the outcomes of win, tie, lose between two models for a given prompt were treated as individual battle records. This method allowed us to combine ratings across all evaluation axes to produce an overall performance score. The results are summarized in a ranking chart, where we observe that our model achieves the highest ELO rating compared to all recent state-of-the-art text-to-image methods at the time of benchmarking. We also present some qualitative results of our generations. Moving on to video personalization, we recognize the importance of generating high-quality personalized videos that accurately reflect an individual's identity. We incorporate personalization into our video generation process, achieving state-of-the-art results as detailed in this section. We describe our innovative model architecture, training methods, and evaluation criteria for personalization, along with quantitative results. For our personalized text-to-video generation model, PT2V, we enhance our existing 30B movie general video model by incorporating identity information extracted from a reference image alongside the text prompt. Our model architecture is initialized from the T2V movie general video weights, and we use vision token concatenation to integrate this information into a unified framework, allowing us to scale the model size. We extract identity features from a masked face image using a trainable vision encoder, followed by a projection layer to align these features with the text dimensions. Our training strategy includes a pre-training phase followed by high-quality fine-tuning. In terms of pre-training data, we focus on videos featuring the same person throughout all frames. We curate this dataset from the movie general video pre-training datasets by filtering raw T2V videos based on captions that include human-related concepts. We extract frames at 1-second intervals and use a face detector to retain videos with a single face, ensuring that the similarity score between consecutive frames is above a certain threshold. This process results in a dataset of millions of text-video pairs featuring a single person, with video durations ranging from 4 to 16 seconds. We categorize our PT2V training dataset into paired and cross-paired data. Paired data consists of cases where the reference image is from the same video clip, while cross-paired data includes instances where the reference image comes from a different video but features the same individual. For paired data, we sample frames from the video clip, resulting in millions of paired training samples, while cropping and segmenting the face area to focus on critical regions. To avoid the model learning a simple copy-paste solution, we also collect cross-paired data where the reference image is from a different video of the same person. We gather both real and synthetic cross-paired samples, ensuring a diverse set of training data. This comprehensive approach yields millions of synthetic cross-paired data samples, maintaining identity consistency throughout the process. Section Summary. In this section, we evaluate our text-to-image generation model using human evaluators to assess text faithfulness and visual quality through pairwise comparisons, ultimately achieving the highest ELO rating among contemporary models. We also detail our approach to personalized text-to-video generation, which integrates identity information from reference images to enhance video quality and consistency. Section: Pre-training recipe. In this section, we outline our pre-training approach for PT2V, which has three main objectives. First, to train the model to maintain identity when generating videos based on a reference image. Second, to create longer personalized videos. And third, to enhance the naturalness and expressiveness of the generated human figures. We discovered that training directly on long videos is not effective, as it slows down the process of integrating identity into the model. This inefficiency arises because the training speed increases significantly with the number of frames, and the connection between reference images and long videos is often weak, complicating the task. In the first stage, we focus on identity injection by training the model with short videos and reference images. We limit the model to 8 latent frames, which corresponds to 64 RGB video frames, to speed up the identity integration. During this phase, we freeze the vision encoder and only train the transformer backbone. We notice that the model quickly learns to align with the reference image, as indicated by the average similarity score. In the second stage, we shift to generating long videos by increasing the number of latent frames, similar to our pre-trained T2V model. This significantly improves the consistency of the long videos, especially regarding background and coherence. In the third stage, we address the unnaturalness often seen in the generated videos, where characters may appear to stare directly at the camera. To enhance naturalness, we train on cross-paired samples, where the reference image does not match the target video. We utilize both real and synthetic cross-paired data and fine-tune the vision encoder to capture more detailed identity features. For supervised fine-tuning, we enhance video aesthetics using high-quality data. We gather a small set of high-quality videos to ensure the generated content is visually appealing. Starting from our T2V fine-tuning set, we collect videos featuring a single person and select a diverse range of human actions. Our final fine-tuning dataset consists of 1,000 high-quality videos with both paired and cross-paired reference images. We evaluate our PT2V models based on 3 criteria: identity preservation, video quality, and video text alignment. The evaluation of video quality includes aspects like overall quality, frame consistency, completeness, and naturalness. To assess identity preservation, we ask annotators to rate how closely the generated character resembles the reference image and how consistent the faces are across frames. For our evaluation dataset, we select 50 subjects not seen during training, pairing each reference image with multiple unique prompts, resulting in 330 image prompt pairs that cover various human activities and expressions. In our results, we compare our personalized movie general video with ID Animator. We aggregate scores for identity and consistency, showing that our method significantly outperforms the baseline across all evaluation axes. We also compare it with movie general video without visual conditioning. Our generated videos demonstrate diverse identities and camera angles, and qualitative comparisons reveal that personalized movie general video consistently excels in identity consistency and video quality compared to ID Animator. Section Summary. In this section, we outline our PT2V pre-training approach, which consists of 3 stages: identity injection using short videos, long video generation for consistency, and improving naturalness through cross-paired samples. Our evaluation shows that our method significantly outperforms the baseline in identity preservation, video quality, and text alignment, demonstrating the effectiveness of our training strategy. Section: Ablations. In this section, we examine the effects of key design choices in our 30B personalized text-to-video training pipeline. First, we investigate the impact of training the visual embedding from a face encoder. We analyze whether training this embedding alongside the video generation task enhances performance. By retraining the 3rd stage of our model with either a fixed or trainable vision encoder, we find that using a fixed encoder significantly harms identity preservation. Next, we look at the use of cross-paired data, where the face image used for generation comes from a different video clip than the one being generated. Our findings indicate that while cross-paired training reduces identity metrics, it is essential for improving facial expressions and natural movements in the videos. Human annotations show that this approach enhances text alignment by over 27% and overall quality by nearly 14%, particularly improving naturalness by about 26%. We also demonstrate the importance of a high-quality fine-tuning stage, which positively affects video quality and text alignment, although it slightly decreases identity preservation due to the inclusion of cross-paired data. As video content becomes increasingly prevalent, the need for user-friendly and precise video editing tools is growing. We introduce Movie General Edit, a model that excels in video editing without relying on supervised video editing data. Our training approach is based on 2 key assumptions. First, that explicitly training for video editing is more effective than training-free methods, and second, that minimizing discrepancies between training and testing scenarios is vital for maximizing the model's potential. To address these assumptions, we implement several training stages. Initially, we train the text-to-video model with a multitasking objective that alternates between image editing and video generation. Although this stage allows for some generalization to video editing, it often results in blurry outputs due to distribution shifts. In the second stage, we introduce synthetic tasks that better mimic multi-frame video editing, which helps refine the model. Finally, we adapt back translation for video editing in the last stage, allowing us to train on high-quality multi-frame videos. Our results show that human annotators prefer Movie General Edit over previous state-of-the-art models more than 74% of the time on the TGVE Plus benchmark. To support the evaluation of future video editing models, we have created a new comprehensive benchmark called Movie General E-Bench, which includes a variety of video editing tasks with diverse instructions and videos, unlike previous benchmarks that were limited in scope. Section Summary. In this section, we analyze the effects of key design choices in our 30B personalized text-to-video training pipeline, revealing that using a fixed vision encoder significantly compromises identity preservation, while cross-paired data enhances facial expressions and overall video quality despite a slight drop in identity metrics. We also introduce Movie General Edit, a state-of-the-art text-guided video editing model trained without supervised data, which effectively minimizes train test discrepancies through a multi-stage training approach, ultimately outperforming previous models in user preference. Section Model. In this section, we present our model designed for video editing, addressing the challenges posed by the limited availability of supervised video editing data. We recognize that training methods often lead to discrepancies between training and testing, which can result in lower quality outputs. To tackle this, we propose a multi-stage approach that gradually reduces these discrepancies. Model architecture and initialization. To adapt our architecture for video editing, we make several modifications. We add extra input channels to the patch embedder, allowing us to combine the latent video input with the noisy output video. This concatenation is crucial for our model. Additionally, we incorporate task-specific embeddings for various editing tasks, such as adding objects or changing backgrounds. For each task, we apply a linear transformation to the task embedding, generating 4 embeddings that we merge with the hidden representations of the text encoder. We also adjust the task embedding by adding it to the time step embedding. To maintain the model's video generation capabilities, we initialize new weights to 0 and use pre-trained weights from a text-to-video model. Stage 1. Single-frame video editing. We start by training the model to use an editing instruction along with a video input during the denoising process. Since we lack supervised video editing data, we utilize an image editing dataset, treating image editing as single-frame video editing. This dataset consists of triplets of input and output images, which we consider as single-frame videos. We understand that high-quality video editing requires more than just accurate editing of individual frames. It also needs to ensure temporal consistency and natural appearance of newly generated elements. Therefore, we train the model on both image editing and text-to-video generation simultaneously. During training, we use a black video as input to the model. We alternate between image editing and video generation batches to speed up training, sampling image editing batches more frequently. We also discovered that using the first frame's positional embedding during image editing led to distorted outputs in video editing, so we switched to using a randomly sampled temporal positional embedding instead. We train the model with this objective for 30,000 steps. Stage 2. Multi-frame video editing. After Stage 1, our model can edit images and generate high-quality videos from text, but it produces blurry edited videos. We believe this is due to discrepancies in training, particularly because the model wasn't trained on multi-frame video inputs in Stage 1 to address the blurriness. We create 2 new datasets that include multi-frame video inputs and outputs. Animated frame editing. We develop an animated frame editing dataset using a video caption pair dataset. We prompt a language model to generate an editing instruction and an output caption for the desired edited image. We then select a random frame from the video and apply a single-frame editing model to generate an edited frame. To create an animated sequence, we apply random transformations to both the input and edited frames iteratively. This results in a series of animated frames combined with the editing instruction. Generative instruction guided video segmentation. To enhance the naturalness of our examples, we introduce generative instruction guided video segmentation. In this task, the model marks a specific object in a video based on given instructions. We collect editing instructions similarly to the animated frame editing examples, but we focus on marking objects in specific colors. We extract segmentation masks for the objects and create the target video by marking them accordingly. Training. We fine-tune the model from stage 1 on these new datasets, using multitask training for 1,000 steps. During this training, we sample animated frame editing examples more frequently than the other tasks. We observe that this stage reduces the blurriness from stage 1, although some newly generated elements in the edited video still appear oversaturated. Section Summary. In this section, we present a multi-stage approach to improve video editing models by addressing train test discrepancies due to limited supervised data. We modify the model architecture to support video inputs and progressively train it through single-frame and multi-frame editing tasks, ultimately enhancing the quality and temporal consistency of the generated videos. Section. Stage 3. Video editing via back translation. In this section, we describe stage 3 of our video editing process, which involves back translation. While our training in stage 2 helped reduce many issues from stage 1, we found that the newly generated elements sometimes lack quality or appear overly bright. These problems likely stem from using model-generated videos in our dataset, which do not reflect natural visuals. To address this, we create a new dataset using real output videos. Similar to stage 2, we assume we have access to a dataset of videos and their corresponding captions, like apples on a table. We use Llama 3 to generate an instruction, such as put the apples in a small basket, and an output caption, like apples in a small basket on the table. We then apply the model from stage 2 to create an edited video based on the input video and the instruction. Next, we filter the generated examples using automatic scores, following the same method as in stage 2. Instead of simply retraining the model on this new dataset, which could lead to repeating the same issues, we adapt a back translation technique from natural language processing for video editing. We prompt Llama 3 to create an instruction that transforms the generated video back to the original, such as remove the small basket and put the apples on the table. We then build a synthetic paired dataset to train the model to clean the original video while considering the potentially flawed generated video and the instruction. This results in a weakly supervised video editing dataset with real output videos. For evaluation, we test our model against two main benchmarks. The first, TGVE+, is a recent extension that, while comprehensive, features low resolution and short videos. To better assess next-generation video editing models, we introduce a new benchmark called Movie General E-Bench, which includes videos of varying resolutions, frame rates, lengths, and aspect ratios. We compare our method against several baselines, measuring its effectiveness in following user instructions, matching the input video, and overall visual quality. The TGVE+ benchmark includes 76 videos, each with 7 editing instructions for tasks like object modification and style change. However, these videos are low resolution and short, which may not accurately reflect real user videos. In contrast, modern video generation models can handle higher resolutions and longer videos. To create Movie General E-Bench, we use videos from the segment Anything V2 dataset, generating captions and filtering based on aesthetic scores. We sample videos uniformly from different score categories, resulting in a validation set of 64 videos and a test set of 128 videos. To ensure realistic editing instructions, we engage crowd workers to write creative instructions for each video and editing operation. Additionally, we collect input and output captions to support clip-based evaluation metrics. Overall, our benchmark consists of 1,152 examples across 6 different editing tasks. Section Summary. In this section, we describe stage 3 of our video editing process, where we utilize back translation to create a weakly supervised dataset with real output videos, addressing artifacts from previous stages. We also introduce a new benchmark, Movie General E-Bench, to evaluate our model's performance on higher resolution and varied aspect ratio videos, ensuring a more accurate assessment of video editing capabilities compared to existing benchmarks. Section: Video Editing Measures. In this section, we evaluate how well our video editing models can change an input video while accurately following the given instructions and keeping the necessary elements intact. We assess our model's performance alongside baseline models using both human evaluations and automated metrics. For the automated evaluation, we utilize key metrics that measure both the timing and visual consistency of the videos. Specifically, we look at the similarity between the changes in captions and the corresponding changes in the videos, as well as the similarity between the edited video and the output caption. For human evaluation, we follow a standard protocol where annotators view an input video, the editing instruction, and 2 edited videos. We ask them to answer questions about text alignment, structural integrity, visual quality, and an overall assessment considering all factors. Next, we compare our model with leading video editing baselines and analyze the significance of our design choices. We assess our model against various baselines, including both training-free methods and those requiring prior training. One common training-free method is stochastic differential editing, which adds noise to the input video and then removes it while conditioning on a descriptive caption. While this method can maintain the overall structure of the video, it may lose important details. In our experiments, we use stochastic differential editing with our base model and perform the denoising for a majority of the iterations. Another approach involves using keyframes to inject information into the editing process. The top-performing methods typically rely on prior training and address the lack of supervised datasets for video editing. We also compare our method to Tune-a-Video, which tunes a text-to-image model for specific videos. Our comparisons are conducted on the TGVE Plus benchmark, and we also evaluate against stochastic differential editing and Runway Gen 3 video-to-video on the Movie General E bench. We focus on various tasks, noting that Runway Gen 3 video-to-video struggles with fine details. Our evaluation results show that human raters significantly prefer our model over all baselines. On the TGVE Plus benchmark, our model is favored 74% more often than the current best model. In automated metrics, our model achieves top results on one metric and performs comparably on another, despite the other model having access to additional information. Overall, our method is preferred over Runway Gen 3 video-to-video and demonstrates advantages in maintaining the structure of input videos compared to stochastic differential editing. Section Summary. In this section, we evaluate our video editing model, Movie General Edit, against various baselines using both human and automated metrics, focusing on its ability to follow instructions while preserving video structure. Our results show that Movie General Edit significantly outperforms other methods in human evaluations, particularly in maintaining structural integrity, and achieves state-of-the-art results in automated metrics, despite some limitations compared to models with access to output captions. Section: Ablations. In this section, we aim to evaluate and measure the significance of our main design and implementation choices. Unless noted otherwise, we conduct our assessments on the validation set of Movie General E bench using the human evaluation metrics outlined earlier. In Stage 1, we compare multitasking with using an adapter. We initially train our model with a multitasking goal that switches between image editing and video generation. Alternatively, we could train an image editing adapter on top of the text-to-video model. This method allows us to keep the video generation abilities intact by freezing the weights of the text-to-video model. However, it requires more memory and 2 text inputs for video editing, a caption for the frozen model and an editing instruction for the adapter. To test this, we create a version of a ControlNet adapter that aligns with our earlier model. We freeze the original text-to-video model and make a trainable copy, applying the same adaptations as before. We then add a zero-initialized convolutional layer after each layer of the trainable model. During processing, the frozen model receives a caption for the output video, while the trainable model gets similar inputs. we combine the hidden states of both models after each layer. We train the adapter on image editing data for 10,000 iterations and compare it to the Stage 1 model trained for the same duration. We assess their image editing performance using various metrics, including distances between input and output images and several clip-based evaluation metrics. We also conduct a human evaluation where raters compare the original image and instruction with two modified images, determining which output better preserves the input elements and follows the editing instruction. Our findings show that the Stage 1 variant performs similarly to the ControlNet variant on some metrics but outperforms it on others. Human evaluations suggest that full model training yields outputs that align better with editing instructions and are more faithful to the input images, indicating that full training supports higher quality editing than the ControlNet adapter. In Stage 2, we fine-tune the model from Stage 1 on an animated frame editing dataset. Alternatively, we could have animated the image editing dataset from Stage 1, avoiding the need for a new dataset. To explore this, we train the Stage 1 model using the animated dataset. Our results show that human raters consistently prefer the outputs from Stage 2, finding them more text-faithful and of higher quality. In Stage 3, we generate edited videos using the Stage 2 model, apply filtering, and then perform back translation training. Here, we evaluate whether back translation is necessary or if standard fine-tuning on generated outputs is sufficient. We follow the same training protocol but focus on predicting the generated video from the input video and original editing instruction instead of back translation. Our results indicate that while back translation slightly reduces text faithfulness, it significantly enhances structure, quality, and overall preference. To evaluate the contribution of each stage, we compare models from each stage with those from the previous stage. Our findings reveal that Stage 2 shows significant improvements over Stage 1, with human evaluators favoring it more than 89% of the time. The benefits of Stage 3 are subtler, with evaluators preferring the Movie General Edit model over Stage 2 in over 60% of cases. Most improvements from Stage 3 are reflected in the enhanced quality of the edited videos, with only a minor trade-off in text faithfulness. Section Summary. In this section, we evaluate the impact of our design choices across different stages of our model, finding that full model training in Stage 1 yields better image editing results than using a ControlNet adapter, while Stage 2's fine-tuning on animated datasets is preferred by human evaluators over simpler alternatives. Additionally, we discover that back translation in Stage 3 enhances video quality and structure, despite a slight decrease in text faithfulness compared to standard fine-tuning. Section: Joint Sound Effect and Music Generation. In this section, we outline our approach with Movie General Audio, which aims to create soundtracks for video clips and short films lasting from a few seconds to a few minutes. Our soundtracks include ambient sounds, sound effects, and instrumental music, but we do not incorporate speech or vocal music. The ambient sounds should reflect the visual setting, sound effects need to align with actions and objects, and the music should convey the video's mood while blending seamlessly with the other audio elements. To handle videos of varying lengths, we develop a single model capable of generating audio based on a video and extending audio for videos with partially created sound. We target generating up to 30 seconds of audio in one go and allow for extensions to create audio of any length. Our process for generating longer videos is illustrated in a figure. We enable audio extension by training the model to predict masked audio, where it forecasts the audio based on the entire video and its surrounding audio, which can be empty, before or after the target audio, or around it. This infilling technique helps correct small segments with unwanted sounds. For sound design, we recognize that users often want to specify how sounds should be added to the video, such as emphasizing certain on-screen sounds or adding off-screen sounds. To give users more control, we incorporate text prompts. Regarding our model, we utilize generative models and the diffusion transformer architecture, adding conditioning modules for better control. We also employ the flow matching objective to train our model, using optimal transport paths for audio samples in a latent space. Instead of conditioning solely on text prompts, we condition on multimodal prompts. We prefer diffusion-style models over discrete token-based models because they perform well in generating sound, music, and speech, allow flexible generation directions, and enable techniques for infinite-length audio generation. Additionally, they let users adjust quality and runtime through configuration. Our Movie General Audio uses the diffusion transformer architecture, which adjusts outputs of normalization and attention layers. A multi-layer perceptron predicts modulation parameters based on flow time embedding, sharing the MLP across layers to save parameters without losing performance. For audio representation, we adopt a latent diffusion framework, where audio data is represented as compact features at a lower frame rate. Our DAC-VAE model provides higher audio quality and sampling rates compared to commonly used features. We also use a fine-tuned meta-clip model to extract embeddings for each video frame, ensuring better alignment between audio and video. We condition on partially masked target audio, referred to as audio context, to ensure coherence in generated audio. This context is represented as a feature sequence and combined with the audio latent features. For audio generation without context, we input a sequence of 0 vectors. Finally, we use text to guide the quality, sound events, and music style of the audio, collectively termed the audio caption. We encode this caption into features and integrate it into our model for conditioning. Overall, we aim to create a cohesive audio experience that aligns well with the visual content. Section Summary. In this section, we describe our Movie General Audio system, which generates soundtracks for videos by combining ambient sounds, sound effects, and instrumental music, while allowing for user control through text prompts. We utilize a diffusion transformer architecture to create a model capable of both generating and extending audio, ensuring that the sound aligns with the visual content and enhances the overall mood of the video. Section: Inference, One-Shot Generation. In this section, we discuss our approach to inference during one-shot generation. During training, we independently drop out each conditioning input, such as video, audio context, and text, based on certain probabilities. This allows us to use a single model by simply altering the conditioning inputs. For audio extension, we face memory limitations and efficiency issues, so we limit our training data to a specific length. To create high-quality, coherent long-form audio for videos that exceed this length, we employ two methods: segment-level autoregressive generation and multi-diffusion. We start by dividing a long video into overlapping segments, assuming we have text captions for each segment. Both methods first generate predictions for individual segments and then combine these predictions. The overlapping frames allow information to flow between segments. We typically consider each segment to be a certain number of frames long, with consecutive segments overlapping by a specific number of frames. For example, in a video with a total of 55 frames, we would have multiple segments, and we denote the text caption for a specific segment and its corresponding prediction. We introduce two methods for extending audio: segment-level autoregressive generation and multi-diffusion, with multi-diffusion generally yielding better results, which we prefer to use. In segment-level autoregressive generation, we generate one segment at a time, using information from the last frames of the previous segment. We have two main ways to pass information: through context conditioning, where we update the audio context with the previous segment's prediction, and through trajectory regularization, where we blend the trajectories of the current and previous segments to maintain continuity. We also enhance this method with segment-level beam search, generating multiple candidates for each segment and selecting the best ones for the next segment. For multi-diffusion, we draw inspiration from its success in generating wide panorama images. This method solves the equations for each step in parallel across all segments, consolidating predictions before moving to the next step. We initialize by drawing from a prior distribution and then split the audio into chunks based on our segment definitions. We merge predictions while ensuring that contributions from each segment are appropriately weighted. We apply soft masking functions to determine how much each segment influences the frames it covers. We note that these functions ensure that contributions from all segments sum to 1 for each frame. This process continues until we complete the flow. We also explore different soft masking functions to achieve smoother transitions between segments, avoiding abrupt changes that can occur with simpler methods. Section Summary. In this section, we describe our approach to one-shot generation and audio extension, where we utilize dropout during training to allow flexible input combinations and implement two algorithms, segment-level autoregressive generation and multi-diffusion, to generate coherent long-form audio from segmented video inputs. We highlight that multi-diffusion generally yields better results by processing segments in parallel, while segment-level autoregressive generation focuses on sequentially generating each segment with context and trajectory regularization for smoother transitions. Section: Model, Training, and Inference Configurations. In this section, we describe our model, training, and inference configurations. Our DIT model consists of 36 layers with attention and feed-forward dimensions of 4,608 and 18,432, totaling 13 billion parameters, excluding certain components. During pre-training, we limit videos to 30 seconds, or 750 frames, and randomly segment longer videos. For fine-tuning, we sample 10 and 30-second segments from the videos. We utilize fully sharded data parallelism to accommodate the model size. The training occurs in two phases, pre-training and fine-tuning, both using the same objective but different datasets and optimization settings. In pre-training, we work with an effective batch size of 1,536 sequences, each capped at 30 seconds. We conduct 500,000 updates over 14 days using 384 GPUs, starting with a constant learning rate of 0.0001 that ramps up for the first 5,000 steps. For fine-tuning, we reduce the effective batch size to 256 sequences, also capped at 30 seconds, and perform 50,000 updates over 1 day with 64 GPUs. The learning rate again ramps up to 0.0001 for the first 5,000 steps and then decays to 0.00000001 for the remaining steps. We accumulate an exponential moving average checkpoint during fine-tuning for inference. We employ the Atom W optimizer with a weight decay of 0.1 and use BF16 precision for both training phases. To enhance inference with classifier-free guidance, we randomly drop conditioning inputs, video, text, and audio, with a probability of 0.2. For audio generation and extension, we mask audio completely with a probability of 0.5 and partially between 75% to 100%. We also independently drop text and video inputs with a probability of 0.1 each. For inference, we use a midpoint solver with 64 steps, finding that other solvers or increasing steps did not improve performance. We apply classifier-free guidance with a weight of 3 on unconstrained vector fields and perform re-ranking with 8 candidates per sample. We set quality scores of 7.0 for sound effect generation and 8.0 for joint sound effect and music generation. For audio extension, we use dynamic guidance with a weight of 3 and multi-diffusion with specific triangle windows. Next, we categorize audio-visual data, noting the complex relationships between audio and visual elements. For instance, some sound effects, like footsteps, relate to low-level objects, while others, like laughter, connect to higher-level semantics. Music can be performed live or added in post-production to enhance storytelling. We classify audio along two axes: audio type, voice, non-vocal music, general sound, and diegetic versus non-diegetic audio. We use an audio event detection model for automatic classification, recognizing that each sample may contain multiple audio types. Diegetic audio refers to sounds that can be heard in the scene and have a causal link to the video, while non-diegetic audio, like narrations or background music, does not. Diegetic sounds can be on-screen or off-screen and can be real or created in post-production. Videos often contain both types of sounds, especially in professional productions. We leverage a contrastive audio-video text pre-training model to assess the likelihood of an audio sample being diegetic based on the corresponding video. This model is trained primarily on diegetic sounds, leading to closer audio and video embeddings when they match. To generate different sound classes accurately, our model learns various relationships between audio and the conditioning input. Diegetic on-screen sounds have a strong correspondence with video, requiring robust video understanding and action recognition. The complexity varies, with general sounds being easier to generate than music or speech. Generating diegetic off-screen audio involves understanding potential sounds in specific environments and the logical sequence of events, demanding stronger reasoning capabilities. Non-diegetic audio relates to the video at a semantic level, requiring deep understanding and reasoning about human emotions. In our work, we focus on generating diegetic general sounds, non-diegetic sound effects, and instrumental music. We find generating diegetic speech challenging without transcripts and omit non-diegetic speech, as it can be synthesized if scripts are available. Given the correlations between video and audio, as well as among different audio classes, we aim to build a model that generates all audio classes jointly rather than using separate models for each category. Section Summary. In this section, we describe the DIT model's architecture, training, and inference processes, highlighting its 36 layers and 13B parameters, as well as the two-stage training involving pre-training on 30-second video segments and fine-tuning with different batch sizes and learning rates. We also classify audio types based on their relationship to video content, focusing on diegetic and non-diegetic sounds, and emphasize the model's capability to generate various audio classes jointly, leveraging complex correlations between audio and visual elements. Section: Pre-training data. In this section, we focus on pre-training data. Our goal is to understand the structure of audio and how it aligns with video and text by using a large amount of data, which includes both low and high-quality audio samples. We outline our criteria for selecting pre-training data based on AED tags and CAVTP scores. We begin by gathering a vast dataset and using the AED model to tag audio events according to the audio set ontology, which has 294 classes. We eliminate any videos where silence is the main audio. The remaining events are categorized into three groups: speech, non-vocal music, or general sound. An event is classified as voice if it includes any speech or singing tags, as music if it contains music tags, and as sound for any other types. This allows for combinations of these categories in an utterance. After organizing the samples by audio type, we use the CAVTP score, which measures the similarity between audio and video embeddings, to further classify the utterances. We set thresholds based on manual checks. We focus on diegetic or mixed audio, filtered by CAVTP scores, along with a small amount of non-diegetic background music. We prioritize general sound, as learning low-level audio physics can be difficult and errors are more noticeable. To minimize visual noise, we apply quality filters to remove videos with text, static images, or low resolution, and we limit video lengths to between 4 and 120 seconds. We also use copy detection embeddings to eliminate duplicate visuals. For fine-tuning, we aim to align our model's output with the expectations for cinematic soundtracks, which differ significantly from general recordings. Cinematic soundtracks are typically recorded with professional equipment and undergo post-production to eliminate unwanted noises and balance audio events and background music. We recognize two main sources of fine-tuning data. The first is a cinematic split, which includes professionally produced clips with both diegetic and non-diegetic sounds, excluding those with vocals. We use an audio-visual classifier and AED model for automatic filtering, followed by human selection. The second source is high-quality audio, which consists of high-quality music and sound effects without accompanying videos. This data is more abundant and helps enhance audio quality. During fine-tuning, we mix cinematic videos with high-quality audio at a ratio of 10 batches to 1 batch. Regarding caption structure, we create captions that include audio quality, voice and music presence, sound description, and music style. We utilize several models to generate synthetic captions for all training data. Audio quality is rated on a scale from 1 to 10, with 10 being the highest quality, based on predictions from an audio quality model. Voice and music presence are determined by the AED model, with voice being a binary output and music represented by a probability score. Sound descriptions come from a general audio caption model, while a music caption model adds details about mood and genre, regardless of whether music is present. We find that combining music probability from the AED model with music captions gives us better control, as the music caption model is primarily trained on music samples. Each audio sample is divided into 10-second and 30-second segments for captioning, and during training, we sample these segments at a ratio of 5 batches to 1 batch. Section Summary. In this section, we outline our approach to pre-training and fine-tuning audio models using a diverse dataset filtered by audio event detection and cosine similarity scores, ensuring high-quality audio and alignment with cinematic soundtracks. We also describe the structure of synthetic captions generated for training data, which includes audio quality ratings and detailed descriptions of sound and music presence. Section: Evaluation. In this section, we evaluate soundtrack generation based on 3 main criteria: audio quality, audio-video alignment, and audio-text alignment. We place greater importance on how well the audio aligns with the video rather than the text, as the text serves only as a supplementary guide and may miss some video details. Additionally, the final output does not present the text to viewers. We summarize our metrics in a table and explore the correlations between subjective and objective metrics in a separate section. For audio quality, we assess how natural and professional the audio sounds. In our subjective tests, we use a pairwise method where raters choose which audio sample has better overall quality. We calculate the net win rate, NWT, as the difference between the percentage of wins and losses for each comparison, with scores ranging from negative to positive values. For objective evaluation, we use an audio quality score predicted by our model, noting that it tends to favor samples with music, so we avoid using it for comparisons between music and non-music samples. We do not use certain metrics like Frechet audio distance or KL divergence, as they are not suitable for our focus on generated videos without corresponding audio. For video alignment, we measure how well the audio matches the video. For diegetic sounds, we evaluate correctness, whether the right audio is generated for the scene, and synchronicity, which checks if the audio occurs at the right time. For non-diegetic background music, we assess how well it fits the scene's mood and synchronizes with actions. We again use a pairwise method for subjective tests and report the net win rate. For automatic metrics, we employ the image bind score to measure alignment between video and diegetic sounds, noting that the presence of non-diegetic music often lowers the score. In terms of text alignment, we focus on precision and recall. Precision measures the percentage of generated audio events that match the text, while recall measures how many audio events from the text are generated. We prioritize recall since the text may not capture all sounds in the video. For subjective tests, raters score precision and recall on a scale from 1 to 5, using a standalone protocol for easier evaluation. To compute the net win rate, we evaluate each model pair with 3 raters. We average their preferences to get consensus scores, which we then average across all items to find the net win rate. We also calculate 95% confidence intervals through bootstrapping. For our audio generation benchmarks, we consider various video sources, both real and generated, and plan to release a benchmark called Movie General Audio Bench. This will include high-quality videos generated by Movie General Video, covering a wide range of audio events, along with human-reviewed sound and music captions. We categorize videos into single-shot and multi-shot types. Single-shot videos are more abundant and diverse in sound effects, while multi-shot videos, taken from short films, offer richer narratives and are better for evaluating music alignment and sound design. We detail the composition of our benchmarks, starting with single-shot videos, which include sources like VGG Sound and our new Movie General Audio Bench. We ensure the quality of these videos by removing duplicates and static content. For multi-shot videos, we use segments from short films, chunking them into manageable lengths for comparison with baseline methods. Finally, we create text prompts for sound effects and music generation using Llama 3, selecting the best captions for each video. We adjust the likelihood of music presence in our prompts to generate audio that fits the desired context. Section Summary. In this section, we evaluate soundtrack generation based on audio quality, video alignment, and text alignment, prioritizing video alignment since it is more relevant to the final output. We employ both subjective and objective metrics, including net win rate for audio quality comparisons and various scores for assessing alignment, while also introducing a new benchmark dataset for comprehensive evaluation of audio generation across different video types. Section: Comparisons to prior work. In this section, we present both qualitative and quantitative results for sound effect generation, joint sound effect and music generation, and long-form audio generation with extensions. We compare our model, Movie General Audio, with 4 open-source models and 2 commercial models for generating sound effects in single-shot videos. Among these, some models accept video and text input, while others only support video. Our findings show that Movie General Audio significantly outperforms all other models in synchronization, correctness, and overall quality of generated audio. Notably, it excels in producing professional-sounding audio, indicating that it generates not just realistic but also high-quality sounds. When we look at sound effect and music generation, we demonstrate Movie General Audio's capability to create cinematic soundtracks that align with visual actions. We evaluate it using a specific setup that encourages joint generation of sound effects and music. However, we find that some baseline models struggle to generate both simultaneously, so we exclude them from our analysis. Our results indicate that Movie General Audio surpasses all baselines in quality and alignment, particularly in joint generation scenarios. For audio extension, we assess Movie General Audio's ability to create long-form audio. We compare it to a simple method where audio is generated for each segment and then stitched together. Although we face challenges due to limited video sources and the difficulty of maintaining focus during evaluations, we still find that Movie General Audio with audio extension outperforms the stitching method. This highlights the importance of smooth transitions and coherent music, which our model achieves more effectively than the alternatives. Section Summary. In this section, we compare Movie General Audio with various models for sound effect generation, joint sound effect and music generation, and long-form audio extension, demonstrating that our model significantly outperforms all baselines in audio quality and alignment metrics. We highlight that while commercial models excel in audio quality, Movie General Audio excels in producing both realistic and professionally polished sounds, and our audio extension method ensures smooth transitions, surpassing simple stitching techniques. Section: Ablations. In this section, we examine key design choices for Movie General Audio, focusing on text prompts, scaling, data, and extension methods. We utilize the 13B parameter model and assess its performance on SGen SFX for generating sound effects. First, we explore how varying the audio quality specified in the text prompt influences the audio output. Our findings indicate that as we increase the specified audio quality, the predicted quality scores improve consistently across both datasets, aligning well with subjective evaluations, particularly up to a score of 6.5. Human raters show a preference for scores of 6.5 and 7.0 for sound effects, where distinguishing quality becomes challenging. This confirms the relationship between subjective quality assessments and our objective quality metric, AQUAL, demonstrating effective quality control. However, the effect on video sound effect alignment is minimal for sound effects alone, while we see notable improvements in sound effects combined with music, where the alignment score increases significantly. Next, we investigate how text prompts can control sound effects and music styles. We find that text is particularly effective in guiding the generation of unseen sound events and can also dictate different music styles for the same video. We also analyze the impact of using text prompts during training and generation. We pre-train and fine-tune two models, one with text input and one without. Our results show that using text captions slightly enhances audio quality and significantly improves alignment metrics. When generating without text prompts, the model trained with text still outperforms the one without, especially in subjective alignment metrics, indicating that text helps the model learn audio-visual relationships. Additionally, text prompts guide the model to produce the desired sound effects, as evidenced by higher clap scores. We then assess the benefits of scaling by comparing models of different sizes, 300M, 3B, 9B, and 13B parameters. Performance generally improves with larger models across all metrics. We also evaluate the effectiveness of fine-tuning. Our results show that fine-tuning significantly boosts both audio quality and video alignment, resulting in a more cinematic feel in the generated videos, underscoring the importance of high-quality data for this process. Furthermore, we enhance our fine-tuning by incorporating high-quality audio data alongside cinematic audio-video data. This inclusion leads to significant improvements in audio quality and video alignment, particularly for sound effects and music generation, allowing the model to better separate different audio types. Lastly, we compare our main extension method, multi-diffusion, with segment-level autoregressive generation and other configurations. We also include a one-shot generation method that produces audio for the entire video without extension. Our evaluations reveal the performance of these methods, with qualitative samples provided for the 13B model. Section Summary. In this section, we ablate key design choices for Movie General Audio, demonstrating that varying text prompts can effectively control audio quality and style, with significant improvements observed in sound effect and music generation through fine-tuning and high-quality data inclusion. Our findings indicate that larger models and the use of text prompts enhance audio-visual alignment and overall quality, while different extension methods yield varying results in audio generation. Section: Text-to-Image Generation. In this section, we discuss text-to-image generation, highlighting how diffusion models have transformed this area. While we cannot cover every model, we focus on the most significant ones that are widely used. The foundational work on latent diffusion models compresses images into a simpler latent space using a variational autoencoder, which enhances training and inference efficiency. DALL-E 3 improves image captioning by using GPT to refine captions, reducing noise in large text-image datasets for better training outcomes. EMU employs a higher latent dimension and fine-tunes a pre-trained model with a small, high-quality dataset to produce professional images. Stable Diffusion 3 enhances generation quality by using advanced flow transformers with a multimodal diffusion backbone. In our own work, MovieGen, we utilize a 16-channel variational autoencoder and flow transformers with prompt rewriting to ensure high visual quality and text alignment. Moving on to text-to-video generation, we note that advancements in text-to-image generation have significantly improved video generation quality and coherence. Following the success of diffusion models for images, they have been adapted for video synthesis. Some approaches introduce zero-shot video generation by adding dynamics to pre-trained text-to-image models. For instance, Direct2Volts uses instruction-tuned large language models to create videos by breaking user inputs into prompts for each frame. Other methods, like Imagine Video and Make a Video, train deep cascades of spatial and temporal layers through pixel diffusion modeling, while some focus on applying diffusion in the latent space for efficiency. AnimateDiff integrates a pre-trained module into a T2I model, and several models, including EMU Video and Stable Video Diffusion, incorporate images as additional inputs for text-to-video generation. Lumiere generates the entire video duration at once using a spacetime U-Net, while Sane enables smooth transitions between diverse scenes and can produce videos of varying lengths through auto-regressive prediction. Some studies have explored noise scheduling to enhance coherence and length in video generation. Although many text-to-video models use U-Net architectures, Snap Video and OpenAI Sora demonstrate the effectiveness of transformer architectures for this purpose. Latte also opts for a DIT instead of a U-Net backbone. Additionally, some works focus on transformer models within an auto-regressive framework. River employs flow matching for efficient video prediction by conditioning on a small set of past frames in the latent space of a pre-trained VQGAN. In our research, we utilize a Llama 3 transformer architecture to train a text-to-video generation model within a flow matching framework. Regarding encoding videos into a latent space, encoder-decoder models have been essential in latent generative architectures, compressing various media types into a lower-dimensional latent space. Latent diffusion models typically use either a standard variational autoencoder or a quantized version like VQVAE or VQGAN, which includes a GAN discriminator loss for better reconstruction quality. Most image and video generation models rely on convolutional autoencoders, although transformer-based models like Efficient VQGAN and VIT VQGAN show promising results. For our movie General Autoencoder, we achieved the best results with a continuous convolutional VAE that includes a discriminator loss. Models using convolutional autoencoders are generally divided into those for images, 2D, and those for videos, 3D. Some models, like Stable Video Diffusion and Video LDM, use an image VAE to encode frames individually, but they struggle to generate long, high frame rate videos due to limited temporal compression. A newer approach involves using 3D or mixed 2D-3D models, such as MagVit, which employs a 3D VQGAN with both 3D and 2D downsampling layers. In our work, we opted for an interleaved 2D-1D convolutional encoder, balancing reconstruction quality with lower memory and computational costs. Notably, some models incorporate causality through asymmetrical padding, which allows for independent encoding of the first frame. However, we found that causal encoding is not necessary for joint image and video generation. Symmetrical padding can effectively serve this purpose, as long as replicate padding is used, a finding also supported by TATS. Section Summary. In this section, we discuss the advancements in text-to-image and text-to-video generation, highlighting the impact of diffusion models and various architectures like latent diffusion models, U-Nets, and transformers. We also explore the use of encoder-decoder models for compressing media into latent spaces, noting our preference for an interleaved 2D-1D convolutional encoder for efficient video generation. Section: Image and Video Personalization. In this section, we discuss personalized image and video generation. For personalized image generation, previous research has mainly focused on two approaches: identity-specific tuning and tuning-free methods. Identity-specific tuning involves training a text-to-image model to recognize a specific identity by fine-tuning it on related images. Techniques like textual inversion create special text tokens for new identities, while DreamBooth uses a few reference images and a unique text token to represent the identity. LoRa techniques help speed up this training process by using lightweight adapters, and HyperDreamBooth further reduces training time by predicting initial weights from reference images. However, a significant limitation of these methods is that they create models tied to specific identities, making it hard to scale for multiple users. To address these limitations, some research focuses on extracting visual features from reference images and integrating them into the diffusion process. This approach allows all users to share a common base model. For instance, Elite converts visual features into a text embedding space, while PhotoMaker merges vision and text tokens for better interaction. Other methods, like IP Adapter Face ID Plus, use face embeddings for identity preservation, and Instant ID adds control mechanisms for poses and expressions. Imagine Yourself introduces a comprehensive model architecture and a new data generation method to enhance identity preservation and visual quality. When it comes to personalized video generation, we face unique challenges. Unlike images, videos require more complex modifications, such as changing poses and camera movements. Additionally, videos demand higher quality in expressions and naturalness due to their dynamic nature, and fine-tuning video models is more resource-intensive than for images. Some methods use pose control to generate videos based on reference poses, but these often rely on sequences from real videos, which limits their versatility and can lead to unnatural results. Other approaches attempt to adapt personalized image models for video generation. For example, MagicMe uses identity-specific fine-tuning for video models, while ID Animator extracts identity from single facial images. Our work also emphasizes identity extraction and control methods, as they are more adaptable for various users. In the realm of instruction-guided video editing, users provide a video and specific instructions for modifications. The challenge here lies in gathering supervised data, leading many to use training-free methods that can be applied to any text-to-video model. Some approaches incorporate additional video features, but they are limited in their ability to control untrained aspects, like preserving identity. The current leading method for video editing, EmuVideo, employs a two-stage training process. It first trains dedicated adapters for text-image to video generation and then aligns these adapters for video editing through a process called Factorized Diffusion Distillation, FDD. This method generates a video through multiple diffusion steps and uses various losses for supervision. We note key differences in our approach compared to EmuVideo. We start training from a text-to-video model and conduct full model training instead of just training adapters. Additionally, FDD's method of backprop-agating supervision through multiple passes is more memory-intensive than our approach, which enhances scalability. By applying our method to the movie General Video, we demonstrate significant improvements over previous results, establishing new state-of-the-art outcomes in video editing. Section Summary. In this section, we explore personalized image and video generation techniques, highlighting the distinction between identity-specific tuning methods, which are less scalable, and tuning-free approaches that utilize shared base models for broader applicability. We also address the challenges in personalized video generation, such as the need for complex modifications and higher quality standards, while discussing advancements in instruction-guided video editing that improve precision and adaptability. Section: Audio Generation. In this section, we explore the topic of audio generation, specifically focusing on video-to-audio generation. Recent studies have investigated this area, primarily using latent diffusion models similar to ours, with a few exceptions that utilize token-based language models. Standard models like Diff-Foley and VTA-LDM employ U-Net architectures that connect video features extracted from pre-trained audio-video and video text encoders. The Seeing and Hearing method introduces a training-free approach, using ImageBind for guidance to help a pre-trained text-to-audio model generate audio that aligns with video. Foley Crafter enhances a pre-trained model by fine-tuning it to incorporate video control, using timestamps to indicate sound and silence segments during inference. Most of these models are trained on datasets like VGG Sound and AudioSet, which have limitations. The quality of these datasets is often poor, as many videos are recorded with low-quality devices, leading to subpar audio and video. Additionally, most content comes from amateur creators with minimal post-processing, resulting in distracting sounds and a lack of well-designed non-diegetic sounds that are essential for cinematic experiences. Training on such datasets restricts the model's ability to produce high-quality soundtracks. Furthermore, previous video-to-audio models are relatively small, typically between 300 million and 1.3 billion parameters. Our ablation study shows that increasing the model size to 13 billion parameters significantly enhances both quality and video alignment. Unlike prior works that offer text control, we also provide quality and fine-grained music control, improving soundtrack design flexibility. Several products, like Pika Labs and 11 Labs, offer video-to-audio capabilities, but they struggle to generate aligned sound effects or cinematic soundtracks. Pika Labs can generate sound effects with video but often produces audio longer than the video, requiring users to select segments. ElevenLabs uses GPT-4 to create sound prompts from video frames, but details about their model are limited. We also touch on video to music generation, where many studies focus on symbolic music generation, like MIDI, which is easier to predict than raw audio. However, this approach has limitations, such as not capturing all musical details and requiring high-quality transcription models. Most existing works extract low-level features from videos, which are often too specific to generalize well. Our work is closely related to previous studies that extract general video features and predict audio representations. We aim to generate both non-diegetic music and sound effects, while others focus solely on music. Additionally, we utilize diffusion modeling to avoid information loss associated with tokenization, addressing quality issues noted in earlier works.